Thank you very much, Professor. Hi, everyone. Hi, crew. It's a big pleasure to be here with you, presenting for the virtual space analog mission of Habitat Marte, specifically for the crew of Mission 87, and also for those who will be watching this presentation in future times. So now I will be presenting for you about the power station. How would be the operation of a power station on Mars? My name is Davi Souza. I am an electrical engineering student at Federal University of Rio Grande do Norte, located here in Brazil. And also, I am a researcher at Habitat Marte Space Analog Station. Well, my presentation will be covering especially these topics of discussion. Just to let you know, I will be covering the same topics that has been proposed by the mission. Okay, so this is just a brief overview about the topics that I'll be discussing in today's presentation, which are design, technologies, resources, management, protocols, and sustainable development. Just to let you know, as my background is in electrical engineering, I will be focusing more on the technological side, just to present you some of solutions that can be useful for future space habitats, especially on power generation systems and electrical systems. Just some initial considerations about my presentation. I always bring this picture just to let you know, to have a big concept about how would be surviving in another planet, how would be the architecture that we'll be dealing with, and the whole habitat will be integrated with the topics that are mentioned in this pyramid. So we have the energetic systems in the bottom, together with the industrial systems. This will be integrated with the building to really deploy and build the ecosystem, which is composed by the atmosphere, the ground, the water, the living organisms. But in the top of this pyramid, as you can see, we have the human factors. So no matter on what facility we will be dealing with and talking about, we need to consider all of these aspects, and the most important one will be the human factor. So my proposals here in this presentation will be mainly focused on how the technological aspect can support the human in space, especially on the electrical side of generation, operation, management, maintenance, and many other aspects on the grid in a future space habitat. Just to let you know, this is a picture that I take it from this paper, minimum numbers of settlers for survival on another planet. About the habitat, I bring here this concept that was proposed by Yash Hato during mission 47. So as you can see here, we have a big overview about our habitat. And just to let you know, the power station is located in this specific area. Let's say talking together with the engineering facility. And this can be a logistic approach, and I will be talking more about during the presentation. And together with the power station, it's proposed the integration of MOXIE, which is an area for oxygen generation. Also together with a solar farm, it's proposed also an aeolic park to be together with the solar farm and integrating and complementing the energy generation, and especially for reliability of the mission and generation in different situations that may be happening on Mars. The current technology, the 1 kilo nuclear power, it's also proposed as a generation unit, and another visual concept of this habitat. Internal design. So all facilities will be presenting a circumference shape with 8 meters of diameter and 3 floors. So some features of this facility, as I mentioned, we have the human factor. So it's necessary to integrate all of the the basic needs that will be delivered for the astronauts. So the dormitories with beds for astronauts, a kitchen, dining room, toilet, entertainment, and also a food microproduction model, which is proposed considering our isolation aspect for now. The electronic systems for a monitoring area, also a battery storage area, and I'm considering alternative generation units inside of the facilities, and externally the main generation units, as I previously mentioned, together with Moxie. So for the design of the habitat, I'm just proposing here. An internal division. As I mentioned, I will be focusing more in the technological aspect of this facility. So just to provide you some ideas, in the ground floor we would have the social entertainment area and a sleeping and toilet also, because this area will be more for the astronauts interact with the other astronauts and having like some visitors in maybe situations that other astronauts will be coming to the facility. And when we go to the first floor, we would have the photobioreactors cultivating microalgae, also a monitoring area, and especially the protection systems, which I'll be also talking better during the presentation. And in the second floor, in the last floor, we would have a battery hub. And the battery hub, it's proposed to have, I will be talking also with more details, but the proposal is to have the most dangerous equipments that need to be like kind of isolated from the crew in case of any emergency. Well, about the technological solutions, the electrical power subsystems will be responsible for generation, storage, distribution of the power, and this power will be like feeding, especially the systems, the life support systems, the environmental control system for in situ resource utilization and other technological systems. Just an example, maybe a system for a surgery in the health center. Just an example. Also the lighting system of the greenhouse and many other systems aboard the habitat. Also, I consider some support technologies. Just an example, automated systems for optimal operational procedures, data collection, detect failures, provide the balance of energy, which is also very important, and take protective measurements. So some of these monitoring systems will be for power statistics, quality of energy, detection of faults, failures, fluctuations, and different situations that may be affecting the grid, and also to monitor the equipment. So batteries, circuit breakers, fusers, protective relays, inverters, and many others, just to have the status of these equipments. So on the computational support side, I consider the use of artificial intelligence, especially for energy forecasting and reports, like to understand the external environment and have an idea, have some predictions on how much energy can be generated, and if it's necessary to start a rationing order or not. Also, some monitoring interfaces for of system parameters throughout the dashboard. So this is especially called human-machine interface, how the human will be using that technology, that interface, to understand the situation, the status of the system. Also, accelerate the maintenance team productivity and shorten repair time by prioritization. So just to give some guidelines about maintenance issues. And a power plant monitoring, as you can see in this picture, a kind of a dashboard, which has the amount of energy produced by the time, maybe some weather issues, some weather parameters, and having some monitoring, some data, and also some performance indicators that may be useful for the system to understand the system. And just an example about data forecasting, the use of artificial intelligence can be really useful, considering some models for weather measurement, also having some historical data on production and understand the forecast of weather. So integrating all of this, it can be useful to provide a forecast aggregator and having some numbers on how would be the production of energy, just an example, in 10 days ahead or maybe a month ahead, depending on the complexity of the model. Another technological solutions. I bring here many proposals for solar farm solutions. Taking this idea of building integrated is very important to Mars, especially to Mars, because it's necessary to save area. And if we have the proper habitat with the capability to generate energy, it can be really useful. Also to cover from radiation and other aspects, it can be useful. So for this building integrated, I consider some malleable photovoltaic cells, and this is another one. It's organic photovoltaics, which I'll be talking more the end of the presentation to let you know more about. Some heliothermic systems. This technology called solar or honeycomb photovoltaics, tracking systems, and also captation by central tower, which can be used with solar radiation, but also with heliothermic system. And just to present you these technologies that I have just mentioned, the left one is the malleable photovoltaics, and the right one is the proposal of the honeycomb photovoltaic. So this is a technology that can be built, that can be integrated in the building, as you can see. But we have small cells, which in each one of these cells we have a small cell of photovoltaic. So it can be useful to generate energy with a higher amount. So because if we have in this small cell, we have a kind of a glass that will be reflecting all of the sunlight in one specific point. We'll be focusing in one specific point, which will be increasing the irradiance in that specific cell. Well, other technologies, as I mentioned, also the central tower. As you can see here, we have some reflectors that will be reflecting their solar rays, and we'll be focusing in one specific receptor. Like if we consider the thermal energy, we will have a pipe with water over this tower, and the water will be heated and generating vapor pressure, and then will be possible to make a turbine to rotate, a turbine rotate and generating energy. Just a brief as the example. And with the same idea, we have also this type of technology. This one specifically uses the tracking system. So we have this design for this photovoltaic, and it can be also reflectors. And we can have here in this central pipe, we can have water also, and focusing all of the solar rays into this specific focusing point. And the tracking systems could be useful also to make the optimal reflectance and putting all the amount of sunlight that can be useful to generate energy in this focal point. And talking about dust storm issues, I have talked about solar panels, but we already know that dust storms can be really a changeful time on Mars. Facing a dust storm can be really challenging. And as you can see here, I bring here this example of the rover Spirit. As you can see in the left picture, we have in yellow, assigned in yellow, the water production, the energy production per hour, so in watts. As you can see, we have a higher amount of energy produced by the rover Spirit solar panels. But as you can see also in blue, we have a less amount, really is low, minimal amount of this measurement called tau. Tau is almost the how much opacity the atmosphere, the Martian atmosphere is. So consider a dust storm. If we have a dust storm, this rate, this specific parameter will be increasing. So as you can see, after 5,100, after this while, we have maybe happened a dust storm, and it has really decreased the amount of energy produced by hours. So that's why it's important, as you can see in right pictures, after previously and after the dust storm. This can be really an issue that we need to overcome and look for other solutions to really produce energy on Mars and guarantee the reliability of all of the systems, and do not depending only on solar panels. Okay. And considering other types of energy, I bring here the power source system for the Perseverance rover, the most recent one, inhabitant on Mars. Let's say like that. The system uses a radioisotope power system called MMRTG, as you can see here, the big phrase. These power systems produce a dependable flow of electricity using the heat plutonium's radioactivity as a fuel, and it can produce about 110 watts at the moment of the launch of the Perseverance. And with the years, the system, the effectiveness of the system will be decreasing percentually. So, and also it's used to lithium-ion rechargeable batteries to make the peak demands of rover activities. Well, and other technological solutions. I have proposed here another idea about energy generation, but also we can just overcome the dust storms with other simple solutions. So this one I bring here is the automatic photovoltaic cleaners. This is a system, just a kind of a robot. This robot is called a copy robot. It has been tested and used in some deserts, and showing how this can be used also for future space habitats. So it works independently and has a water tank, but the most interesting thing for Mars is that this technology can also emit a jet of air to remove the dust waste. So it can be really useful if we consider the importance of water saving on Mars. Other solutions, this is more a theoretical thing, but the wind energy can be also useful. So if we consider that it's a dust storm, we have a lot of rates of wind speed on Mars. So this wind energy can be really also can be an alternative for this period of dust storms. So that's why I have mentioned the solar farm together with a system of wind energy. It can be not the wind energy won't be the main generation unit, but it can be a support unit. So considering some ratios of wind speed collected by Vicky Lander, as you can see, the top amount of 30 meters per second. A turbine with 40 meters high can produce up to 300 kilowatts. So this is a big amount of energy, and can be really useful if we consider that the solar panels will be out of the bounds, let's say like that. And for now, the most recent proposal by NASA, also, it's the kilopower reactor. using sterling technology, also called crusty. As you can see in the right picture, is a titanium radiator with a sterling converter having uranium to be heated and generating energy. So it's a technology that was designed to be safe, long-lasting, reliable, and the most important one, scalable. So considering the scalability, also energy efficient and compact, but considering the scalability, in 2017, NASA has tested this system and has generated about 100 watts of electricity, but this can be scaled up to 10 kilowatts and even megawatts. So it can be the main energy source of energy on Mars, but also, as I mentioned, we can have alternative generation units that will be supporting all of the grid. Just another pictures about the kilopower nuclear, some proposals and concepts. And talking about the battery hub, as I mentioned, this will be a kind of a critical area of the power station. I'm proposing that kind of isolated from the crew because it will be a higher amount of energy and also an area that is really dangerous for the astronauts. So we would have a power storage area with a lot of batteries, also some batteries, heaters, and radiators. Just to let you know, consider the temperature of Mars. It's really necessary to have the heaters because if we have a kind of temperature that is too low, the batteries has chemical compounds, and these chemical compounds can just start, how can I say, decreasing their performance because it won't be in the right temperature. So it kind of it will be freezed, let's say like that. Also some capacitor banks and maybe some FACT devices. These two ones are mainly for energy fluctuations, like to overcome these issues and really made the energy generation efficient and the energy consumption also, avoiding some harmonics and disturbances inside of the grid. Especially considering like the high performance systems and technology that will be aboard the whole habitat. Also a better recycling area I'm considering also because, as I mentioned, there are chemical compounds that it's necessary to deal with. So it's necessary to find alternatives, to look for, okay, this battery is not useful anymore. How can we reuse it? Or maybe do some kind of recycling practice with this battery. Also some inverters and converters, which, as you can see this picture, these one in white, and this mostly for energy conversion. So transforming alternate current in direct current and vice versa. FACT device, as I mentioned, it's a technology that it's becoming really common in the electrical grid, the worldwide electrical grid. As you can see in this left picture, it's a solution made by General Electrics, so one of the biggest companies in the sector. And as you can see, it's huge, but consider the amount of energy that has been produced for nowadays worldwide. These systems can really increase the performance of the electrical grid and also transmission systems. For Mars, this will be not that effective in the initial phase, but I consider this type of technologies as a first step to avoid, especially critical situations on the grid on a possible electrical grid on Mars. And I bring also this small algorithm just to let you know how it works, FACT device works, considering increasing the power demand. So an example would be motor, we can have a motor for in situ resource utilization. You can have a system that will be demanding a higher amount of energy that is common demanded by the habitat. So this will be causing some unstable operation in the power system, and the FACT device will apply an optimization tool with an algorithm to avoid this disturbed cases, deriving optimal solution in voltage stability, enhancement, and cost minimization. So this is really important if we consider the optimization of an electrical grid on Mars also. Other technological solutions, alternative generation units. I bring here other possible solutions that can be useful to generate energy. If we consider the case that everything is going wrong, let's say like that. If the kilopower is not working, maybe having a dust storm, and how we can produce energy with other systems that are not that main system, that main generation units. So I bring here some proposals: the electromagnetic floor, as you can see in this picture, using some electroimams, and using inductance, let's say like that, that to produce in each step, by each step, an amount of 5 watts can be useful because astronauts will be also walking throughout the station. Microalgae as a source of biofuel. I will be talking more about microalgae also in next slides. Mechanical energy of treadmills and bicycles, like using the exercise activities of the astronauts to generate also energy, and wastewater to energy facility, which I'll be also talking right now. So as you can see here, I bring just 2 ideas of alternative power plants. The left one is a proposal for a bicycle, how the energy would be generated. And as you can see, we'll have bank of batteries, converters. So as I previously mentioned, and there's another one, the wastewater treatment facility, transforming this wastewater into energy. So as you can see, we can have the sludge from the wastewater and transforming it into a biogas, and also in organic matter that can be useful for soil enhancement. So we can have these 2 applications of this energy. Other technological solution will be the interplanetary communication systems. This will be just to let you know, this is a topic that is not common covered during these presentations about Powerstation, but because we are familiar with that for here on Earth, but we have a kind of a network, a bigger network with our whole solar system, and like also in like far and deep space, also in longer kilometers away. Let's consider the Voyage one. The free space optics, using optics lasers to provide the communication. As you can see in this picture, we have in red some free space systems, and also the deep space optical communication. This will be using laser communication system to increase the performance and efficiency, and it's also stabilize the data that can be sent like for by an orbiter, let's say like that. And I bring also these 2 concepts, just in the left one, just to let you know how simply kind of works. We have the laser, we have some lenses, and the signal is pumped into this laser. It can be really useful in many ways, like avoiding noises and other stuff in the deep space, and also increase the amount of data that can be transported. So in the right picture, as you can see, a simple operation about, let's say, on the Perseverance, with the Perseverance, the communication, it can be They will be having an orbiter on Mars, and the rover will be talking, let's say like that, will be communicating with this orbiter directly with this orbiter, and then this orbiter will be sending the information to Earth. And just like, previously with radio frequency systems, it was demanded an amount of months to have a higher quality picture of Mars. So, and now we can have this picture almost instantaneously. This was provided especially for these optical communication systems. Resources to be generated in situ. Some algae powered fuel cells. This is a technology that I found in the research, some previous research, that was developed a biophotovoltaic cell, which can produce an amount of 0.5 watts per square meter. It can be also useful, considering that algae will be generated inside of the photobioreactors. And algae can be also useful for other aspects. So it can be not only a biofuel, but also can be an edible biomass, can be providing the CO2 to O2 conversion, especially supporting the MOXIE operation, and also can be useful for effluent treatment. I bring here in this picture some ideas about green technologies and the integration with space technology. So algae is already mentioned by NASA to be used in future systems, in future habitats on Moon, Mars, and beyond. Other resources to be transported. So the systems for production of oxygen, fuels, feeder circuits, and network optimization to reduce consumption costs. So as I mentioned, let's say it's necessary to be transported the FACT device hardware, the MOXIE, a minimal amount of technology to build the MOXIE, let's say like that. So this can be really necessary. Mainly of the resources will be these systems to produce these features. Regarding MOXIE, the characterization is a prototype and experiment useful delivered to Mars with the goal to characterize the size and morphology of atmospheric dust to verify the effects on the operation of surface systems and produce molecular oxygen from atmospheric carbon dioxide on Mars. So just to let you know, the Martian atmosphere has an amount of 96% of carbon dioxide. So having a kind of machine, an area to make this generation, it can be really effective to generate oxygen for the whole habitat. And some pictures about MOXIE. The left one, you can see the design of the prototype that was sent aboard the Perseverance rover. And the right one, as you can see, the process that are involved inside of these systems, which use a kind of an electrolysis to produce, to really transform the CO2 to convert the CO2 into O2. Talking about the management, the organizational structure of the habitat, I'm considering talking especially on the grid side. I'm considering connected infrastructures also between the engineering center, allowing redundancy systems. So just to let you know, as I mentioned, it can be considered a logistic approach for the location of the power station together with the engineering center. So we can have a redundancy system considering some protection systems also in the engineering. So before the energy go to the whole habitat, it passes first for the protection systems of the power station, and then it goes to the protection systems to the engineering center to really go to the rest of the habitat. So the mainly protection systems will be aboard the engineering and also the power station. the engineering center, and also at Powerstation. The professionals will be capable to conduct experiments aimed at grid structures or systems maintenance, specific research related to energy system in collaboration with the engineering center. I'll be also talking more about that on the 3D printing protocols. I will be letting this specific topic to be talking later. And waste management, like analysis of what was discarded, if it's possible to conduct an equipment recover, having a reuse logistic, and also some disposal considerations, some disposal requirements also, to see if how it will be, and also having some guidelines for disposal, like just to consider, let's say, photovoltaic cell. We already know that it can be useful, can generate the life cycle of a photovoltaic. It's an amount of let's put 20 years. So after these 20 years, what we do with that solar cell? Just disposal in the environment. This is not effective, especially to Mars. So talking about the grid, the proposal for this grid, as I mentioned, we would have the alternative generation units, the main generation units, and this will be a kind of covered helmet by a monitoring area in the protection system. So all of the information about the generation units will be passing through all these systems, and then go to the power station, like really go into the grid. After that, will be deliver energy for the social area, the food microproduction and sleeping area, and then for the battery hub. So the battery hub will have the power control, the higher amount of power control with batteries, inverters, and other technologies that will be having that higher amount of current and voltage and power at all, and the recycling area of batteries, and also the electric systems, like other device equipments, materials. And I also consider an emergency decoupling. The idea of the emergency decoupling, I'll be talking also with more details on the protocols of safety, but it's just to, in case of any emergency at the battery hub, let's say, okay, a chemical compound of a battery has just spreaded in the environment. Like, it's necessary to really start the decoupling of this system, of this hub, with the rest of the habitat. Just an example. Another example would be like, okay, we have a battery, it has just exploded. It can be, it can occur like a harsh situation, but it can also occur. So if it's happened with one battery, like the whole system will be compromised over there, and it's necessary to avoid that, to spread to the other systems, to the rest of the power station, and then to the rest of the habitat, especially to guarantee the safe of the astronauts, like guarantee that they will be safe and it will be not affecting their health, their lives. If happens something with the system, okay, we start the emergency decoupling, and then we can keep with the other generation units, avoiding the batteries and looking for other solutions to storage the energy. This is just an example. Position profiles and duties. I consider two permanent positions. It's the power manager and the chief engineer. Like, this will be the main astronauts that will be over there conducting the main activities. As you can see, the power manager will be more on the management side, conducting good practices, awareness, development of protocols, guidelines for the other stations also. And the chief engineer will be that one qualified to conduct in situ activities, and also install the equipment and conduct the maintenance of these equipments. Other functions to be engaged. So these functions can be switched by each one of these positions. This is a kind of my approach. Like, okay, we can have the functions. We have the leader, the sub chief, we have system analysis and maintenance officer. So depending on the goal of that specific period of the habitat, let's say, okay, we are in the phase of deploying the energetic system. So it will be more effective if we have as a chief, the chief engineer, like conducting the activities and focusing the operations of the power station in the installation of the system, the deployment of the electrical systems. But if we are in a situation that all of the operation of the electrical of the grid is okay, and we are just looking for some optimization tools, some guidelines, protocols, understand the data, it will be more effective if we have the power manager being the chief of that system in that specific period. So the chief will be that one to delegate functions, give instructions, establish schedules, and promote the rotation between the respective habitat, with like having astronauts also coming to the power station to understand more about the electrical grid, and considering the current situation that we are dealing in our mission, that everyone is isolated, it's necessary for each one of us have a minimal understand the knowledge about the grid and how the systems works. That's why it's important to have this rotation. Some basic features to incorporate in the national training program: the idea of sustainable human presence in space, support long-term effects of isolation, practices to reduce costs and technical risks in overall vital system. This is the main important one, and also the main approach of my presentation now today. And also courses focused on basic understanding of the handling and maintenance of electrical systems, analysis of risks, failures, and having some reports, some monitoring reports. Also conduct meetings for crew decision making. And I also consider some simulations and how to develop new skills to overcome emergencies based on situations identified at Mars. As I mentioned the example of, okay, we doesn't have the power hub anymore. It's a situation that maybe the astronauts was not expecting, but it happened. And how for now to overcome this emergency situation and to provide another battery hub or having another storage unity or technologies to store that energy. That's why it's important to develop these new skills based on the situation. And just to let you know, on Mars, based on what we know now, the situations that we are considering for Mars are specifically based on data that was reported by rovers, and also some studies that has been conducted here on Earth. So it can be identified many other situations once the astronauts arrive on Mars. Well, I bring here some YouTube videos to suggest to you the solar ore, the honeycomb that I have mentioned, the Mars nuclear reactor, also about MOXIE, and the other one is about the Copia robot, that one that I mentioned for cleaning the dust into the solar panels. And I also bring this another video. It's also a video from Nat Geo, National Geographic, which talk about generating power on Mars. It's a really good video. I bring just some screenshots just to just to show you that it's almost what I'm proposing here. Some different systems, different electrical systems, and source of energy generation. And talking about resources, for 1 week, it can be considered considering the energetic needs of the habitat. According this NASA administrator, it will be necessary an amount of per week, an amount of 40 kilowatts of power. And just to let you know, this calculation will be based on the dimensions of the energy supply, water supply, heating, air conditioning systems, and also environmental control. This will be determined by the number of inhabitants and the amount of vegetation. Talking about food, the diet and amount of food to be consumed by each astronaut will be determined by his weight, his height, the biotype, the routine. But I'm considering here an amount per person, 1.1 kilograms of a daily consumption. This is not a number that I'm just like giving to you. These values I have taken based on some results about on the article on the paper greenhouse production analysis of early mission scenarios for Moon and Mars. It was a research that was conducted on Eden ISS greenhouse and considered the best approach to meet astronaut daily demand, the biomass consumption, but also provide a minimal biomass storage status. So if we have some critical situations with food, it's necessary to have a minimal storage status of food, water, the main resources, and also energy, I'd say like that. Considering the potable water, I consider, based on what we already know here on Earth, 3 liters of water by person. It can be changed once the astronaut arrive on Mars, and considering these 3 liters, a weekly consumption of 42 liters of water. Guidelines to other facilities. The power station will be responsible to give some indicators of consumption and control of energy use, providing economy practices, and also training the other astronauts into these economy practices to be added in the astronauts' routines, providing some basic guidelines and training for handling and preventive maintenance of electronic equipment. As I mentioned, it's really important to have that minimal knowledge. Smart reports, especially to correlate the different parameters, variables of the system, and how we can maximize the energy efficiency. Having protocols for energetic guidelines and warning about failures and emergencies. Considering the protocols and routines about the power station, I bring here the idea of tracking systems to have notifications related to deviations and irregularities. This is really important. Like, okay, I can give you a personal example that happened yesterday. I was installing a lighting system into a greenhouse, and the system has a kind of a watchdog that happened a short circuit into one lighting system, and the circuit breaker just has activated, and like the system was not able to restart without any monitoring of the engineers over there into my current job. So just a brief example. That's why it's really important to have this idea of watchdogs, to have this okay, if happens something, it's necessary to as soon as possible. Remote monitoring systems, especially for the vital systems, on the life support and also on the environmental control. And with that, I consider this kind of architecture, let's say like that, conceptual architecture, that the grid, the generators, and the batteries will be monitored by a controller. This controller with sensors will be provided by sensors, and also will be understanding the energy consumption and the energy demand of other infrastructures, also monitoring high loads and the protection systems. And this will be also having a machine operator interface, especially to have the system status. Regarding protocols of safety, I consider some fast isolation procedures. As I mentioned about the emergency decoupling, in case of any failures, faults, short circuits, lightning strikes, which is really common in sandstorms and dust storms, it's necessary to start the emergency decoupling. So we can have some levels of decoupling. So if you have a situation that, okay, we have fire over there, how we can avoid this fire spread in the station? So maybe just doing an evacuation of the system, like opening that battery hub to the surface of Mars and just remaining with that minimal structure for living and also with some alternative generation units, like to avoid this fire to spread in the station. But we can have also some emergency decoupling, like on the grid. Okay, we have kilopower that has broken, or like has also happened a short circuit or a lightning strike. A lightning has struck on the kilopower, so it's necessary to decouple that from the grid in that time, and previously have look and then look for the protection equipments, of the plants, to avoid these losses, to avoid widespread losses, and then start the process to check the status of the equipments, and then conduct go to the site that happened at something and really see if everything okay, and if the system really is not really working, it's necessary, if necessary, establish in order to deactivate that specific generation unit and activate the bank of generators and of alternative generators and backup batteries. And considering system recovery, conduct an AVA to monitor and assess the affected site, perform the inventory of losses and the recovery schedule, some guidance, inform the other mission members about the maintenance and repair of energy resource. Maybe this will be affecting the whole grid. Like, okay, we cannot have that specific system functioning right now because we are conducting this maintenance, and it's not that feasible to have that system operating because that system is vital for us. So just an example. And check up for restart, reinitialize the system, or initialize it, the new system, like see if it's really possible, and check if everything is okay. Made a previous checkup before really putting the system on the grid again. Protocols for occupancy. This is on the basic needs, the astronauts' basic needs issues and features would be the alternation of monitoring routines, like just to have different tasks among the astronauts, switched by the astronauts, not conducting the same activity every day, all day long. Socialization practice proposed by the health center, relaxation areas, conduct physical exercise, games, and also having some operational activities inside of the greenhouse, having some human plant interaction, and also with the micro production model. Consider the food micro production module. The idea is to operate with the guidelines received from the greenhouse facility. This is a kind of a presentation that it's my personal background about greenhouses, space greenhouses. And me and Professor Julio has the opportunity to present this paper called Agriculture in Mars, Habitat Marte Finding, during the IAC last year. It was conducted virtually. It was a virtual edition. And we have proposed on these studies, based on our experiences on biohabitat greenhouse at Habitat Marte, we came up with these protocols for a food production system, and it can be useful also for this food microproduction, which are the routines. So we have the management, the maintenance, the recycling practice, and also harvesting and processing, and also some activities on analysis, diagnosis, and search circularity assure the fidelity of methodologies, having some orientations, and detect possible failures. And these protocols, the idea is to ensure the food logistics, risk management and prevention, provide monitoring reports, and also implement the waste management. About the protocols for 3D printing, the idea is to have a cooperative work between the energy center and the engineering center for the production of, like, as I mentioned here, eco device, organic electronic device, equipment coverage, shelters, and also conductors and filaments. As I mentioned in the beginning of the presentation, the logistic of the energy center, the power station with the engineering center is really important, because we cannot have it's not that feasible to have a 3D printer inside of the energy center. But it's, of course, it's really necessary to have a 3D printer in the engineering center. So for the power station, it's better just to have this conversation with the engineering center and just to provide maybe some technologies, some materials that can be useful for the grid, for the power station, and for the energetic systems. And I bring also two pictures for you, just to let you know. The last one, it is a circuit, some filaments that was 3D printed, and also some cover materials for electronic device. So as you can see also in the right picture. I also bring here the algae 3D printed. So this is really interesting. This is a recent research. I have found this paper and I thought, oh my God, this is really interesting, because we are kindly producing food, like 3D printing, food, energy, oxygen into one single solution. This is a really interesting solution. It's a solution using microalgae printed on bacterial cellulose. This is another bioprinting technique to print this microalgae into this living resilient material capable to conduct photosynthesis. And it can be considered a sustainable living material because it's biodegradable and recyclable nature, and also a new oxygen production material, so it can support MOXIO activities. And the 3D printing solar panels, especially on the organic photovoltaics. I'm considering here for the 3D printing photovoltaics, low cost manufacturing. It can reduce the cost by 50%. Many materials are viable, and also it can have a lot of flexibility, allowing that idea of building integrated and malleable photovoltaic systems. Low weight, this is really useful if we consider the payload, and also proper disposal. It's organic, it's easier to conduct any kind of disposal or reuse practice, and also possible to be 3D printed, these organic photovoltaics. So 3D printed solar panels are 20% more efficient than traditional panels. So this is a really useful solution. It has been implemented nowadays, but it can be also really used for future space habitats. And considering now on the spin-offs side, I bring here some solutions to be applied on Earth based on my presentation. And just to let you know, all of the things that I have talked here can be really useful to be applied on Earth. Space can be really useful to Earth in many, many aspects. So some concepts that I have talked today that can be useful and to be applied as a solution to Earth is the idea of a self-sustainable electricity, structures with efficient resource saving, eco-friendly structures, especially. Also some delivers with lowest possible handling and better performance for the smart grids. We are these areas increasing even more, especially with IoT technologies, artificial intelligence, and many others. So the smart grids are becoming more familiar, more common to us, and also some environmentally friendly technologies with carbon footprint reduction. So just to have an idea, this is a solution that uses organic photovoltaics on the roof of a building. And so while allow the light, the sunlight goes into the building and avoiding like some lighting systems to be operating. It uses sunlight and while the same time produce energy. So each square meter can avoid the each square meter of an organic photovoltaic can avoid the emission of 120 kilograms of CO2 per year. This is awesome. Some guidelines to be applied on Earth: sustainable energy production, creative ways to deal with solar energy issues, new technologies, especially to improve safety and reliability, easy assembly and maintenance, optimal procedures, keep the confidence related to the control of power and its protection systems. This is really important because we have migrated on the power protection systems. We have migrated from that system that are not smart, and we are moving to new systems, to new technologies and new solutions on the grid, on the current power grid that we have with smart protection systems, especially to guarantee this confidence on the grid. Reuse of materials, energy consumption management, and some investments also. And the impacts on SDGs, the Sustainable Development Goals. So we can ask, how does the operation of the infrastructure results infrastructure and results impact, and its results impact the Sustainable Development Goals, which are? So I have just highlighted here for you some of the SDGs that we can relate, that has some relationship on what I have mentioned for today, on what I have mentioned in this presentation. So we have the SDG 7 with affordable and clean energy, decent work and economic growth, industry, innovation and infrastructure, responsible consumption, and the main important one, the climate action. So we need to know that space is here to us to collaborate and also help us to overcome the climate change, how climate change is affecting our world, our planet. So it depends on us to be agents of transformation. We know that space can do that for us, and we really need to spread this information, this knowledge, and show people, hey, space is not here only to waste money, waste time and energy, but it can be a useful solution. It can be really useful to us to support on the sustainable development, on a regenerative economy, and even more. So I bring here the sentence. We are now open to a new horizon of technological deliverables that can support sustainability while reducing the negative impacts of climate change. Space exploration not only generates knowledge for human living off Earth, but also help us to find solutions to societal problems and inspires people to act for a more humanized and sustainable society. So these are my references. And thank you very much for your attention. It was a big pleasure to me to be here talking with you for the crew. And for those who will be watching this presentation later on the YouTube channel of Habitat Marte, feel free to contact me on social media and also by email. Thank you very much.